the next four vector that's of interest to us is the potential four vector. And it's got to include the potential. So I'm going to start off and write the first term in the four vector as the potential, and then try to figure out what the rest of them should look like. So we want something that's going to obey this. Make sure my 4 pi's are in the right place, all right? We want to obey that, all right? And we want it to transform, yes.
And we didn't define the Laplacian in 4-vector form.
We haven't done that yet.
Yeah.
Oh, wait. I didn't?
You didn't.
Oh.
You wrote it up there.
You wrote up that you were going to do it, and then you forgot to.
There.
In English?
That's a dot product of the covariant and
Yes, and contravariant forms. And I have to, actually, let me check to see whether I put them in the co and contra correctly. No.
because you have to have the right dimensions to matrix multiplication.
Yeah.
So that's the same.
You've got to be pointing in the right direction, have the right dimension. Right. And so the wave equation is this. That's the wave equation. Which is that's probably over. No, that's right. Okay. C squared. Yeah. Actually, to make it look like that, I should write it here. Really? Yeah. Close. But that makes this look like that.
Great. So does that mean that this potential also satisfies the properties of a wave? Like,
The electric field does, I'm sorry.
Oh.
So we actually haven't gotten to the wave equation. But the yes. When you take a derivative of the potential, you get the electric field.
okay.
Gradient potential. All right, so that's our definition of, this is, sorry, the 4 vector. Look, it's called the D'Alembert, right? And I can't spell it.
The what?
It's what
Down
Joker
there.
showed us.
It's down there.
There's a U, but it doesn't matter.
Or some version
Down there.
of that thing that I just wrote. That almost looks right.
Why is there a mu there instead of like a 2 or something?
Yeah, here's the problem. This it's a 4 vector, not a 3 vector.
So is the symbol actually a square, or
It's a square, it's a square.
no? But is that actually the symbol, or Is that actually the symbol, or did you just make that up?
No, that's actually the symbol.
Oh,
All right.
Why do we thought that was a mistake in printing on textbooks?
No,
That does it.
Say that again?
I always thought it was a mistake when on printing in textbooks or something.
It could be, sometimes it is. I've noticed very frequently using my math processor, my math writer on Word, that, so I use math type. And when it, some people who get my files then convert them and they end up with a symbol that looks like this. And they always want to know what that's still a closed circle, a closed path, so it's all good. But that was not the original intent, I'm sure. It just converted it. All right. So, we want to construct a what we're going to call the potential four vector. It should satisfy the Poisson's equation. I was going to say Laplace's equation, but no, Poisson's equation. And all the quantities should appropriately transform under Lorentz transformation. Right? So I'm just going to say, well, I've got some four vector, but I've got to figure out what the components are going to be. But the first one, I'm going to make the scalar potential. And then the other ones, I haven't defined yet. And what we're actually going to do here in the next, well, probably into the next class, but is figure out what form that must have and what form the field must have that would give rise to that, such that it obeys the rules of special relativity and transforms the way that it should transform Lorentz transformations. What should those A's actually look like? Right, so we can start out and we can say that in the steady state, the four derivative, or the Lambertian actually, operating on the first term here, which is the A0 term, okay, should give us the first term. Did I miss something here?
the Q and N naught are back.
Q and naught. Oh, there's my density. Okay, this is really rho in here. Yes, that's good. Gamma Q and naught is rho. So I could rewrite that without the gamma and sort of hide the transform. So it's rho C. Okay, and this one I'll just leave gamma Bx, By, Bz. Or,
Then you
and I need a
move the Q's around.
over Q. No, I have to put the Q inside then. Q, Q, Q.
And the N knots.
And naught.
It's getting a little crowded in there.
Yeah. Okay. All because I just wanted to be sure I wrote rho there. All right? Because I want to look at how the first term behaves here. All right? And the first term over there is going to be, we want it to be 4 pi over C J0. And J0 then gives me 4 pi rho. So my the Lambertian operating on the potential. So I'll write that over here. mu 5, because I'm going to get a naught to be 5, does give me 4 pi rho. Okay, so we've got the physics of Gauss's law and the Laplacian operating correctly. Gary, you had your hand up. No?
I'm not curious, but
Oh,
Hi.
Gary.
No, man.
If, sorry, when you originally wrote the square, you had
The Lombardian.
The Lombardian, you had the order of those dells flipped.
Oh, I will try to make sure that I write it correctly in the online notes.
How much does the order matter?
Order
It's whether you're
matters.
taking the column vector times the row vector times the column
Okay.
vector.
Just the
Yeah.
other one.
So the
one
order
that makes it
matters
big.
a
It's
lot.
the one that makes
Whichever
sense.
one gives you the dot product.
And it's going to give me a scalar out the other side.
One gives the scalar, one
Otherwise,
gives
I
a
get
matrix.
something messy out the other. Actually, I can't actually dot them properly.
Before you wrote the subscript first and superscript second.
Yes, and so that was the question, and I am not sure,
He derped.
right? I'm suffering a stolar moment here.
The column vector needs to be first and the row should be second.
Okay.
Column first, row
I'm going to
second.
continue randomly switching them, and then I'll try to make sure it's correct when I actually post the notes. Okay?
My apologies to everyone on YouTube.
Yeah, I just realized this is sort of public, isn't it? But I haven't looked. Last time I looked, there were, the first video only had like 3 views.
They're up in the teens now.
Oh, uh-oh.
But how many of those teams are people already in the class?
I actually expect someone in this class to take one of those lectures and auto-tune it. So that I sound like Carl Sagan. Correct.
Oh.
How many of you have actually seen the Carl Sagan auto-tune? Not seen, heard. Yeah, okay. The rest of you should just Google Carl Sagan auto-tune.
I'll have to put a link to that in this video.
I think that there's a Stephen Hawking auto-tune as well. All right. So we want this 4 vector to be Lorentz invariant, right? So we should get the same potential, the same physical potential, no matter what frame we're observing it in. All right. And in order for that to be, this was the Laplacian, basically, right? The Poisson's equation. And in order for it to be invariant, because basically, if you think about it, depending upon the direction that you go, the Lorentz transformation mixes up the first term with the second, or the first with the third, or the first with the fourth, depending upon the direction of the transform. It jumbles them, okay? And so that means that each of these terms has to obey the same relationship. So I should be able to write that I know that this has got to be true, if that's true. A1 equals 4 pi over c, J1, and so on, J2, J3. Okay? They've all got to apply. And so I'll just say, okay, all of them got to be true. And that satisfies, because they all transform in the same way. They're all, if all of the terms of the 4 vector transform the same, obey the same relationship, then this is going to be Lorentz invariant. Okay? Now we want to figure out what the form of that A vector is. That 4 vector is. We have this, all right, so we've already said all the terms have got to obey this, but we have one extra constraint that we need to add to this, which is a continuity equation, or conservation of charge. So we can add that. So we want to obey both of these sets of equations with whatever four vector that we create over there, all right? And there are actually a variety of ways to do this. So we're going to impose some additional constraints in order to make the A's obey both of those relationships. And one of them that works is this. We make P nu A nu equal to 0. We make that so. Okay? And we construct an A that obeys that. And this condition is actually called the Lorentz condition. And that will give results that are consistent with relativity and electrostatics. Yeah.
Is that only for the a sub x, a sub y, a sub z, or does that include?
That's all of them.
Wouldn't- Okay.
So we set that to be the case. So, okay, so now you're asking if those are the time and space derivatives of the potential. How can that be? It's a sum over all derivatives.
Oh, okay,
Okay,
that's not.
so that enforces a relationship between phi and the other. That's not d by phi.
Okay.
That's all the other terms as well. All right. So what this condition does is it enforces a relationship between phi and the other terms under Lorentz transformation. Okay. Ohanian has another way, which he doesn't give a name, right? Which is to create an equation, a relationship like this. So we've got, that's a set of derivatives of the potential, right? But I could construct an equation which will give us this transformation, right? By by combining my derivatives in this way. Okay. That's U's and U's are just placeholders. We just sort of go through them, but these two are the same and that one's different. Okay. And now I'll construct in the same equation. Oops. Nu, nu, a, nu. And this, it'll turn out that we can make this obey charge conservation. This does obey charge conservation as well, right? And this has the same overall form as that. So that's just another way of satisfying the charge conservation relationship while obeying this. Yeah.
Is that a J to the nu, or is that a different symbol above the J?
That's a new.
Okay.
They're all new.
They're all new symbols.
Yeah.
Minus one for mu symbols.
Yes.
All right, so the electric
Minus
field that
these
we
ones.
know
Other than that, the rest are all new.
And that one's
is del A0, and I have to think for a moment about, I'll put a minus sign in there.
Yeah.
Or it's also writing it. The But that's only the first term. Okay, so that gives us a field. We want to ask what other fields come out. Should I write that over here? D sub mu is equal to, someone remind me, it's got to be 1 over c d by dt minus d by dx minus d by dy
The,
minus d by
that's the,
You
dz.
didn't put negatives in it the first time you gave it.
the negative, sorry, for the, that's the with the
Oh.
minus signs. is
Oh, yes.
contrary.
Depends upon covariant or contravariant form.
That's, now you have the covariant.
Covariant, I want contra.
But you have the mu such that you have a covariant. You
I want,
you have a mu for a contravariant mu.
Okay, so.
there you go. Okay. So,
I hope everyone was able to follow that.
yeah, for a steady state field, this produces the electric field. All right? That set of derivatives produces the electric field. But we actually have, if we were to operate d mu on a mu, we've got 12 other terms. There's 16 terms that could come out of that. Out of d mu a mu, but I have to decide where to put the mu. I think I want it here, but someone is going to correct me, right? But I'll just tell you that there are 16 terms that I could have there, 4x4 matrix, right? That 4x4 matrix is going to be called the field tensor. And some of the terms we already know, they're going to be the electric field. But there are a whole bunch of other terms which are the derivatives of those unknown A1, A2, A3. All I said was that we've got A1, A2, A3 over there. I didn't tell you what they were, right? The only one that we know is that one, and that one's got to produce the electric field. So, what I could write in 3-vector form is that Ek, so this is just a 3-vector E1, 2, 3, right, is part of a much bigger tensor. And the bigger tensor we're going to call the field tensor. And Ek is actually Fk0. That's the first set in a much larger tensor.
So would that be a 3x3 tensor, F?
That one is, but we're going to work with a 4x4 because that you see here I wrote, these are the components of the electric field in in 3 dimensions. Okay, so that's the terms that we happen to choose over there. But there are 13 other terms besides these that we could, in principle, have. Yeah.
For the expression for the electric field, you have the gradient, and then you have the partial with mu. Wouldn't that involve a time derivative? So you would get a 4-dimensional electric field?
This is,
Here, if I write that, yes.
he's doing the.
I'll do 3-vector there. Okay? I want that to apply, and now I want to have a 4-vector version that obeys all the 3D rules, all the time-independent rules, but gives us all the other time-dependent components that are going to come in later on.
Also out of time.
Okay,